So actually, means after doing that temperature boundary condition, the cylindrical coordinate. So next condition could be a flux boundary condition, and that's actually quite common in case of heat transfer in a cylindrical body, because most of the time you are passing a maybe a hot fluid or cold fluid inside the tubes, and being a fluid actually, so fluid have very low thermal conductivity. So most of the time you have here the heat transfer from fluid to metal surface is by means of convection only. So for that, this convective heat transfer coefficient for time being, let's say we have taken this steam something. So this is convective heat transfer coefficient of the steam, and you have its temperature also, and how far away this metal surface is there. You have Ri here. After that, this metal surface itself have some thickness, and outside of that you have a heat transfer coefficient actually, and that is also open to atmosphere. Sometimes open to atmosphere, sometimes you have a multi-wall actually cylinder, generally not used, but these days people may use maybe successive heating. You will have maybe three concentric cylinder, maybe four. So generally we have heard only double pipe heat exchanger, but you will have multiple of them, because in that case you can serve the so many purposes in only one compact geometry. So that is means another aspect. So let's say this is a typical case of heat transfer through a cylinder by means of convective heating, or maybe cooling, depends what do you need. But outside of that, you have a atmosphere. From there, you don't want any sort of interference. Let's say you want only this purpose is just to heat transfer from a steam to a fluid flowing inside this in a means annular space. So for that particular case, what do you need? Actually, you don't need any sort of losing of heat from outer cylinder to the atmosphere. So that's one way. Another way that's means how can you control that? So you can again put some insulation type of the layer on that, or maybe sometime that's one means. Another way that if you can change the outside surrounding atmosphere, generally it's not possible. So maybe you can put a means outer cylinder with a gas which have very low heat transfer coefficient and fill the gas inside the cylinder. That could also be possible if you have. So suppose these are the conditions. You have heat transfer coefficient inside. You know everything here. Outside, you know everything. So previously we have solved for temperature boundary conditions. So here also you will get same thing, that you need a temperature T naught, and you know need a temperature at R naught, which is Tn plus 1 actually. Now these are the here T naught and Tn plus 1 are unknown, that need to be actually calculated in terms of given data. So given data for you are Ts and Hs, Ri, Ta, and Ha. So you have to somehow convert this T naught and in Tn plus 1 in these variables, okay? As we did in case of heat transfer through a metal ball, a metal bar. So let's say for this one here, so this is the previous conditions would remain same. Only thing you have to apply your means convective flux, and you have to maintain the means balances by conductive flux. So at R equal to R naught, so let's say you have this is your flux here, R equal to R naught, at R equal to Rn actually the outside burn. So you have this one here, Ha1, Ha2. Now if you will expand these equations, and if you will solve it, you will get your T naught would be in terms of this is coming in terms of T2 plus 1 upon Ta1, and again your Tn plus 1 is coming in this particular format. So this particular derivation I am leaving to you. I hope you will get it. Will you get it or not? This is just you are just doing here the nothing here at the time being. You are also discretizing this boundary condition only, right? Hello.
Yes, sir.
Yes, sir.
So you
Yes,
are
sir.
also discretizing this boundary condition and this boundary condition, and once you will rearrange that, you will get these are the expression for your T naught, and this is the expression for your Tn plus one. I hope you will get it easily, right?
Yes,
Yes,
sir.
sir.
Okay. So once you have it, after that you have to substitute back in your previous equations, which is actually I can show you here. So if you say your previous equations are let's say for where is your T naught. So here actually, so in this you can substitute that and rearrange it, and that's one. Then after that you can rearrange in this at this particular place. You have to just put again Tn plus one and rearrange the matrix actually. So if you do that, you can reach actually till this particular point, or you can directly go to this matrix which you have already formulated, this one. And here you just put expression for T naught or T1 and then the rearrange the matrix. That's also one way to do it, but this is slightly disturbing way compared to putting in that equation only. So once you did that, let me show what matrix you will get now. So if you'll do that, so you will just like this. So you have the substituted expression here, your expression of T naught here, right? This is what I have shown you just now. After that, rearrange it and take all known parameters to the right hand side. So this everything is known here. This particular side, you know the K, you know the C. C is actually your the difference point distance. E transfer coefficient is known and the TA1 is also known. So this is your now boundary condition actually. Now same thing you did for Tn plus 1. So this is the expression for your Tn plus 1 here, and again rearrange it. So you will get this one actually. Fine.
Yes,
So
sir.
this is your first equation in new format now. This is your the last equation in the new format. In between part would remain same actually without any change. So let's see the what is your final matrix. So your final matrix would look like this. You have this first term would remain same. Only second term has been changed here. This one. And in between body of the matrix is also the remain same. Your means off diagonals are also same. Main diagonal is also same. Only in last row, this is again changed at this particular place. So by slight changing in your previous code, actually whatever you wrote previous one, uh, you have to just enter this particular expression for that. I hope you can do it easily, right?
Yes, sir.
Yes, sir.
Everybody has made all previous codes by their own, or somehow you are not able to do that. Is सभी का बन गया code के नहीं? That
Yes, sir.
somebody has
Yes,
some
sir.
problem in that.
Yes, sir.
Okay, so
Yes,
if
sir.
you are able to make it is very good then. So you have this, you have to generate this matrix, and this is your A matrix. This is your unknown temperature here. So these are all means unknown temperatures. And now this is your boundary condition matrix. So here you got, I think, this particular term extra, I think, compared to previous one, right? So you have 1 plus 1 upon 1 plus K by 2C HA1 into TA1. So once you have this, now you can, once you have generated matrix, just take A inverse and then you will get the solution there. Right, now I can tell you that how to generate this matrix again. So Again, you have the generated this, so you have a I loop there. You are directly writing this is your main diagonal all the time, which is not changing. So minus 2 Ri upon C square. From I equal to, if I equal to just 1 only, so you are just writing this equation only. This is your second element of matrix A. This is your boundary condition, first element actually, okay? So you have fixed I equal to 1 here. Now from I equal to 1 to I less than n, you are generating, these are your off diagonal elements. This is the left side one, and this one is your right side one actually. Then at I equal to n, again you want to define your second last element of the matrix, which is this one. And this is your last boundary condition actually. So this you have wrote in this way. So these you will just see 1, 2, 3, 4, 5, 6, 7. So practically you have 3 loops actually. So 3 if conditions, and this will generate your entire matrix. Okay.
Yes, sir.
Yeah, so if you will generate it, and then you can write your MATLAB code and all this, and take care in the defining in each and everything with the unit. So this is always a primary condition. So then these are your means the steps just to generate your Ri or elements which we have just wrote in previously in terms of syntax. Now you have write in terms of now your programming language. Just you have put only stars and powers only. That's all. The rest of the things are same. Okay.
Yes, sir.
So
Yes, sir.
once you did that, you got a program completely, then you have solved it, and after that you are calculating heat transfer rate. So this is from your computational program completely. So once you have solved it by this program, now obviously you want to compare with your analytical solution. So because wherever analytical solution is possible, we should always go for that. So these are analytical solution expression just for temperature. Then you have calculated error. Then again heat transfer rate for that, and then you have calculated error, and then you want to plot everything in the same graph. So by putting this command there, by putting a hold on command, so it will plot. This is calculated by you. This is calculated by your analytical solution, and then compare it. So this is just a display and temperature. What do you want to display here actually? So combined plot of temperature, something in everything in one means error at uh, secondary y-axis, temperature on y-axis, primary y-axis. Are you are you able to use these commands, secondary axis, primary axis, by these commands way?
Sir,
Hello.
sir, yes, sir. So can you explain these commands, please? Actually, we are able to plot, but just the simple plots, not.
Yeah, simply plot again. So here, what you have here, this is axis actually. So you have bottom axis is all same. Whatever you have here, first one here, so this will go to the primary y-axis. Whatever you have in the second variable, it will go to the secondary y-axis. So you will have this axis and this y, and bottom axis is same. So first one is the radius, what you want to have here. Okay.
Yes, sir.
Okay.
Yes, sir.
So the radius, then you have temperature, then you have so radius, temperature. So this would go first. It will plot this primary y-axis and primary your bottom axis. So first two is this one only. Second, you have radius and percentage. So radius is again your same the primary x-axis, and this whatever you have the next command percentage absolute error, it will go to the secondary y-axis. Okay, fine.
Yes, sir. Yes, sir.
So this command is being used to make your both the y-axis actually in the same graph. Then rest of the things are the label actually. What do you want to give on your x-axis here? So this is what you have here. Primary one x1, and what do you want to give your y label one? So that's what you want to give their temperature there. Okay. The primary y-axis, you want to write the temperature. So this is what is the temperature. Rest of the things are just a syntax for that particular command. Nothing we are doing here. Only thing we are the writing this particular place here, temperature we want to write here. Then you want to define how much should be its font size and the font weight. You want to have bold or let's say a normal. So if you want to put a bold here, you have to just put bold here. And then color, and then you want to color here black. You can make it red, green, yellow, whatever you feel comfortable. So, so if you write in MATLAB here the plot by axis and all this, just put a help command there, help and plot by help space plot by. You will get everything there with the example. So that is the beauty of this MATLAB. Actually, you need not to remember anything. Whatever you need, just put a help space, whatever you want to help. Let's say plot by, labeling, everything. You will get everything there with a example. Okay. And just change according to your convenience there. This is again just to you want to label is secondary y-axis. So that's what you have here. So here that you want to plot there, absolute error there. Rest of the things are same. Okay. So today you try to use these commands actually. So these would actually help you just to avoid your editing later on. Okay. So then again you want to define your color, your how what color you want to give. Let's say H1 you want to give this one, H2 you want to this. Line style you can change the line style there. So line style, let's say you want dash here, you want dot here. You can change their thickness also, how much width you want, 3 or 4 or 5. It will become thicker and thicker. Then color also, you can keep on changing the color, that what color you gave your actually this side one. So x1 x2, so that way. So y1 by 2 practically, ax1 2 is your y1 by 2 actually. So let's see what you have here. So this was a problem statement for this particular case study. So we have a length L, inner radius R1 equal to 1 centimeter, outer radius is 5 centimeter. Conductivity is given 10 watt per meter per degree Celsius. Temperature and convective heat transfer coefficient or inside gas is 250 and this convective heat transfer coefficient 8.17. Outside you have surrounding atmosphere, so at 35 degrees Celsius, whose convective heat transfer coefficient is 24 watt actually. So we want to generate temperature profile for this. So by taking all these conditions there, so this is the expression for analytical temperature. I hope you would be able to drive it.
We'll try,
Yes.
sir.
Yeah, so you people should try to do the derivation for this here. I hope you will get it as we got previous one. Only intention is that just find the derivation in terms of known variables here. So everything should be known. I mean, nothing should be in terms of T naught or Tn plus 1 because those are not known to you. You only know the surrounding atmospheric gas temperatures and heat transfer coefficient and your position, radius you already know because there you want to calculate, correct or not? So just keep on changing and arranging your equation till you get your expression in terms of all known variables. That is the only logic behind that. Fine.
Yes, sir.
Yes,
So
sir.
once you will calculate that the heat transfer rate is the nothing but is minus Ka dt upon dx. So once you have temperature differentiated with respect to R actually dt upon dr, so you will calculate that only, right? So based on that, this is being calculated. Now, this is just a thing which I wrote here that you have to always do this error means analysis, how many points you have taken, what happens if you will keep on changing the points. So let's say we have taken 100 points, 200, 400, 800, 1600. And based on that, the maximum error was keep on decreasing in this particular way. So we have just fixed up here the 1600 points in this particular case here. Now, this is what your actually temperature profile there. So you got the radius here, bottom, you got a temperature here, and absolute error this side here. So absolute error, you will say that variation of the absolute error is just changing from zero point 0.07 to, if you will say here, let's say highest one may be 0.085, something like that, correct? So you can say your absolute error is fine actually. So if you can increase more number of points, if you can minimize it further, is well and good. Fine.
Yes, sir.
Yes, sir.
So next we will talk about in sphere. So just wait for that. One minute.